Okay, today I'm going to have a look at the first part in the series on a tube supply. It's a vacuum tube supply. I'm going to start with this unit in the centre here. Obviously vacuum tubes are a great kind of power supply when working in Tesla-based research. I use vacuum tubes a lot in a variety of different configurations, and it's nice to have a standardised unit which you can use a lot of different configurations for. I mean, you can see I've got here two valve boards on the bench. One is using a quad 811A and the other is a dual 833C board. And originally the tube supply, I designed and built the tube supply in order to be able to take different valve boards on the top. I wanted to be able to flexibly and quickly be able to change from different valve configurations with the experiments that I'm undertaking. So it was a natural progression to build something that could drive various different types of tube board. And as I said, this is the first part. There are really three parts to this. So there's looking at this unit, which provides the heater and the grid or screen bias. There's the tube boards that actually go on top, and then there's also a plate supply. Each of those will essentially form different parts of. I'll write those up, provide circuit diagrams. As I normally do on the pages, so that anyone interested can take those and run with them. So I'm going to be going over this unit. We were looking at two of the tube boards today. I mean, there is also a 4400A board with a pair of iMac 4400As and also an 810 board, dual 810. Those are the four main boards that I currently use. I'm going to be going over this. I will demonstrate it quickly with experiments. On this side, we're just using the high voltage supply that's already described on the website. That's going to be providing the high tension. That is not actually the plate supply that I was referring to. The plate supply is a dedicated 5 kilowatt power source, which I'm going to be going over in a lot of detail. The experiment here is just a single cylindrical Tesla coil. It has a feedback coil on there, so we're going to run this in series feedback mode, and it simply has a single wire load. The object of this is not actually really the experiment, but actually looking at the tube supply itself. Okay, so getting into detail on this, this unit is designed for being used in a rapid prototype environment. So it's a kind of situation where you want to have a lot of control and a lot of adjustment. It's not intended to be used as a day-to-day industrial supply. It's very much a research and development type power unit. I have added various features that I'll show you during this video, which allow me to modify the characteristics, easily interchange different tubes, tube boards, and also how these things are interconnected. As well. So, for example, if we have a look at the output board for the tube board, that has a whole set of high voltage terminals and jumpers, heater, grid, plate, which allows me to I can easily remove these jumpers, determine what I connect to, how it gets connected. Currently these two are connected in parallel. So I've got two 833Cs with the heaters connected in parallel, the grid and the plates. So they are acting as a dual unit. Also on the back, it allows me also to again configure everything that I want. I'm going to go through in detail what's on there, and then of course all the adjustments, various controls that allow me to set the various biases. If we look at a tube supply first of all in more detail, so this is a quad 811A. So this is a board designed to be put on the bottom. If I just put that in front of the camera, we can see the 4 fans underneath there. They actually pass airflow up, collimated through these tubes and over the valve tubes. So it's a very nice way of doing cooling. I do the cooling on all of the valve or the tube boards like that. Obviously there is inputs and outputs at the back. There's the patch board for actually connecting how the valves are configured. And I also, on these two, because I use these as a series feedback oscillator, I have a grid bias control as well. Very much the same configuration with the 833Cs. They've got fans underneath here. They have these tubes which help to collimate the air up over the glass bulb of the tube itself. And that airflow makes a considerable difference, and it makes a considerable difference when you're running at high power as well. The 811A board, that's nominally, you can run that up to about just over a kilowatt it can sustain, where obviously there's quite a bit more power you can get out of the 833, the dual 833Cs, and also at a much higher plate voltage. So these, obviously we can run those up to 4 kilovolts, whereas the 811As really somewhere around about 1 to 1.5 kilovolts on the plate. So this unit is got 2 sections. It has a heater section at the bottom here, and then it has a grid screen bias section. So it can be used for biasing the grid, or it could also be used for biasing the screen if one's using a tetrode like the 4400A tubes have a screen grid as well as the ordinary grid. And then that also becomes useful in biasing that. So I'm going to move the camera position now, so it's facing face on onto the front of the power supply, and then we'll have a look in detail at the various controls. Okay, so I've adjusted the camera so we can have a close-up look at the front panel. So this section at the bottom here, this is the heater section, and this section is the grid screen supply. So it's quite straightforward. The heater, basically, the heater is a 12-volt, 300-watt toroidal transformer. Now, open circuit, that will provide about 16 volts. Obviously, it's 300 watts. That's going to drop nominally down to 12 volts. And obviously, we need to cater here for a very wide range of different configurations. Like, for example, the 833Cs on top of here, they are 10 volts, 10 amps each. So put 2 in parallel, that's now 10 volts, 20 amps that we want to supply for the heater for those 2 tubes. Whereas the quad 811As, that tube, for example, a single tube is nominally 6.3 volts at 4 amps for the heater. So with 4 of them in parallel, if that's how we've got it configured, we'd ultimately want to get 6.3 volts at 16 amps. So and obviously different tube boards have different requirements. Plus also we may want to only use one of the tubes or configure the tubes to run differently with each other, and therefore we might want to adjust some of those parameters. So we need a very flexible heater control, and we accomplish this by using a variac. So this is a nominally 1 amp variac. Obviously this is UK line supply at 240 volts, and by adjusting this we can adjust the output of the toroidal transformer, which is then connected to the heater, the heater circuits. We also have a soft start here, so this is full, this is in soft. What that means is that if you had it preset, let's say we'd set for the 833Cs, we'd set the 10 volts 20 amps. Now when we turn on from cold, there's going to be quite a sudden inrush of current into the cold filaments, and that can, if done many times, obviously can shorten the life of a tube filament. So by putting it in soft, we basically add a resistor into the primary circuit of the heater supply, and that actually restricts or reduces slightly the amount of current that can flow in the secondary when you first turn on. So in that respect, in effect, the resistor is just is in the main supply. There's a voltage drop across that in the primary circuit, so the voltage across the transformer is reduced, and hence the voltage output of the heater supply is reduced, and hence the current flowing in the filament circuit. So after they had warmed up and everything like that, we would switch to full, and then the characteristics, the current would go back up to where we had nominally set it. Now, obviously, if we're using a variac like this, then essentially we can adjust it anyway. So I can keep it on full, and I can wind it up slowly, little by little, until I'm happy with the bias point that I reach. Now, to measure these things, we have AC voltmeter with 2 ranges, 10, 20 volts, full scale, and also we have a digital AC ammeter. Now, the digital AC ammeter, although it's not so useful when you're actually running a high tension with lots of RF around and things like that, it's very useful to initially set the current accurately for the heater circuit, and that's very useful to be able to make small adjustments and then to set one's heater current to a very accurate position and see, of course, how much voltage as well is developed across the heater. So quite straightforward. The heater supply really is just a transformer with a variac and some measurement of voltage and current. The grid screen supply is more sophisticated, but ultimately it is designed really to give you an output, a stable output of a bias voltage that you can adjust. And in this case it was arranged so that it could be adjusted anywhere from minus around about 700 volts to plus 700 volts in grid mode, or in screen anywhere from 0 all the way up to 1400 volts. Now the reason that is it's got a high voltage transformer there, so again we have a variac which feeds what I call in this case the tank supply, and I'll come on to the reason why that is in a minute. So you have a centre tapped high voltage transformer. Nominally there's 2 windings there, 500 volts each. They're connected in series, so for the grid we can take a centre ground point, and that gives us a positive negative output. Obviously open circuit, that peak is going to be around about just over 700 volts, so 500 normally times the fact that it's RMS specified to 500 volts, and that the peak bias output obviously is going to be higher than that. Now, in order to get the fine control, I mean, it's all very well to set the transformer at an output where you want it, and that charges a capacitor bank inside, so it stabilizes that output, and then you want very fine adjustment of that. I mean, grid supplies, you might want to adjust it just plus or minus 10 volts, or you might have it biased right down at minus 150 volts, and you want to adjust that slightly, say 10 volts either way. So you need fine adjustment. So on the side, actually I'll come to that, let me just turn this slightly, make sure we can see it. This is actually the grid bias adjust, more positive, more negative. And in here we've got a large 150 watt resistor, variable resistor, rheostat, actually very similar one to the one at the top here, which I'll come to in a minute, and that allows you to, depending on where you've set your tank voltage, that allows you to set the output bias very accurately. So for example, if I set a tank voltage of say 100 volts, so the high voltage transformer is producing 100 volts, I've then got plus or minus 50 volts available on my tank capacitors, and that is now fed directly across that rheostat, where I've got a very controlled output there. And we've also arranged so that the biased output can be with these locked switches here. These are lock switches, so they can't be moved, which is important, because if you were to move these, then you start changing the bias positions. So you can take the output of the rheostat from just the negative half of the center tap transformer, flip them up. You can take them from just the positive part of the transformer. That would give you 0 to 700 volts at full tank. That, for example, would give you 0 to minus 700 volts. And if you want to work on positive and negative, then you can flip them to positive and negative. So you are actually now across both secondary coils of the grid transformer. So that allows you to configure how you want to run the output. Internally, there is a ground reference switch, so that determines whether the negative output, or the black terminal negative output on this unit, is connected either to the center tap or to the lower end of the lower secondary. So, for example, for a screen supply, you might have that attached to the lower negative end. For the grid supply, where you want plus or minus output, you have that attached to the center tap, and that's an internal setting. There is a switch inside, which I will show later. So setting this back, both down, gives us 0 to minus 700 volts at maximum tank. So if I was to turn the tank fully all the way over, then that would provide a tank voltage of up to 700 volts. I can then adjust that by adjusting the bias on the side here, measuring the output as I go. So if we look at the measurement output, so we can show several things on this, on DC volts and DC milliamps. So we can look at the tank, we can look at the negative voltage, and we can look at the positive voltage. This really, out plus and out minus, just switches the polarity on the meter. So we can use a single meter like this accurately to display either a negative or positive voltage. And if we put it here, then we see what the output of the tank is. We can also we can scale the range. So for the tank, we can look at 500 volts and 2 kilovolts, full scale deflection, and obviously for the output we can set the resolution down right accurately down to 20 volts full scale, all the way over to 2 kilovolts. Normally I have it set around about 100 to 200, and then I use I'm adjusting the bias, say for the 811As, somewhere around about minus 50 volts, minus 40, minus 50, depending on what type of system I'm setting up. If I'm biasing it to run as a grounded cathode linear amplifier, then I'll set the grid, wind the grid up slowly until I find the right bias point before I put my RF signal in. If I'm running it grounded grid, for example, then obviously I don't need to worry about the grid bias. I can leave that part off. And also when I'm using it as a feedback oscillator, I also don't need to use this part as well. I can use that as a screen instead. So the transformer in there is, as I said, it's a 2 secondaries at 500 volts, 250 VA transformer. So those two in series give nominally 1000 volts RMS at 250 milliamps, which is more than adequate for the biasing of the kind of tube boards that I'm using here. So that's the front panel, and we've looked at the adjustment on the side here as well for the grid adjust, this one. That's the centre point of the rheostat. Now let's have a look at the output panel at the back. If I move it into the top as well, so we can see the tube supply. Let's move it a little bit closer. Actually, move it further away, better. And just adjust slightly so we can see the tube supply at the top. There we are. Okay. So this is how it's configured. Again, this is for rapid prototyping. So setting up tube circuits flexibly, quickly, wanting to change configuration in the middle of an experiment. I like this using these high voltage terminals where if I want to, for example, disconnect the heater from ground, I can just remove that jumper. Like, for example, if I wanted to put an SCR in there to switch cathode supply, then I can actually take that out and take the two wires out across my SCR with my control circuit, and then I can do modulation of the cathode. So being able to configure these things quickly makes an enormous difference. So starting from the bottom, this is obviously the line supply in. We've got the input, main line fuse, plus an on-off. That brings cuts power completely for the whole system. And then we have an output where devices can be chained together. So in other words, I can take that supply out and feed it into another unit that I might be using. Then there's a switchable fan unit, twin fans. They draw in air from the back, and then on the side there are holes both sides on here where the air can escape at the front. Then there's the output board. So this is the low voltage. There's a 15 volt switch mode power supply, small switch mode power supply in here, which I use to power the fans, and also provides low voltage up to the tube board for any low voltage elements that you might have there, like the fans, for example. and a auxiliary output as well, a ground. Then this is the output. This section here is the output of the grid or screen supply. So the positive, a negative, and obviously the earth terminal as well. Once again, I'm keeping everything earth. So this here is my ultimate reference for both the grid supply and the heater supply are in this case reference to earth. And then of course my heater supply in this section here, there's obviously fairly large terminals. We're talking about high current supply here, and that feeds the heater circuit up to the tube board. The tube board itself has corresponding terminals. So these are terminals now which involve the various connections to earth, to grid, and direct access through the red terminal here to the grid. So the grid is connected directly here. This is a feedback from the feedback oscillator parts I've got on the side. I'll come to those in a minute. The negative in this case is not required and is not connected, but is there in case it is required in another configuration. And obviously the heater inlet terminals as well. So that's the rear. Of course, it's very easy to I mean, I can unplug all these. I'm going to show in a minute how you actually change a tube board. But let's, before that, have a little bit more of a look at the tube board. I'll just adjust the camera for this. Maybe I can just go up. Okay, so there's the tube board. Obviously this is the 833C, the dual 833Cs. The back panel for the input panel. This side panel here, we can see the rheostat, and that's actually in parallel with some high voltage capacitors, which are part of the feedback oscillator when it's connected correctly with the feedback coil. And we can just see that out of the picture. Let me just bring that in. That's a feedback coil there that picks up the oscillation from the secondary, feeds it back. This circuit can be used to adjust and get that optimum point. You can adjust the rheostat there to get the optimum grid oscillation. And that forms a very useful parallel mode series feedback oscillator. I mean, I use that a lot in the experiments. I've talked about it a lot on the website itself. And then we have the various connection to the patch panel. So here we can see these are the plate connections to the 833C. The grid behind that, heater at the bottom. This obviously has got a high frequency suppressor on there, so basically to stop high frequency oscillations coming back down into the tube, cause flashover between the grid and the plate. So this acts as this inductor wrapped around a power resistor. This is a 22 ohms, 20 watt power resistor there. Provides some current limiting, and also this inductor will become a high impedance at high frequencies, basically prevents high frequency oscillations coming back down through the experiment down into the tube. If we can have a look at the patch panel output, so here we've got the heater line. The black lines on there show what is hard connected. So here is the heater from the negative terminal at the back, and the patch there basically connects it directly to the tube. So both tubes have their heaters connected. Same with the yellow ones are the grid. The red and black here are the input points for the feedback coil here. So I've got that specially connected to the rheostat on the other side, which basically allows for the grid adjustment of the grid feedback. and then obviously adjustment of its self-oscillation. And the plates are then connected in the same way. So here's the common plate line, and each of the plates for the two tubes is connected to that. And that's all of the parts. Now, the other thing also you see, it's built in a wooden case. Wood is great as a prototyping, working rapidly. It's easy to work with. It's easy to cut out, with the right tools, and there's various things that you need to do for making panels. It's all very easy to work with. Wood is quite good with temperature as well, so it's quite able to absorb, for example, temperature in the toroidal coils, that kind of thing. I mean, classically, years ago, valve systems, valve units were often made in wooden cases and Bakelite cases for those kinds of things. So I like to use wood. I mean, obviously it has pros and cons. Disadvantage of using a wooden case like this is that you don't have common earth points, so you have to make sure that items that need to be earthed, like for example connections for transformers, for the casing of a transformer, or other items that need to have a metal case that connects to earth. Normally with a metal chassis like a rack chassis or other type of chassis, you will very easily be able to make all those connections directly through the chassis itself. You don't have that in this case, so you do have to take extra care to make sure that those things that need to be earthed are wired up correctly to the earth, to the line supply earth, and also of course the screening both from radiation internally and externally. You don't have that facility with wood, whereas with a sealed metal case, obviously you can got much more control over the screening of spurious signals. Now, in a prototype research and development environment, I don't believe that makes a great deal of difference when you're working with Tesla coils. When you're working with coils at high tensions, high voltages, with high currents, especially when you're switching, all that kind of thing, you are creating so much external emitted radiation, high tension fields, all of those kinds of things, that whether it's in a wooden case or not doesn't actually make a great deal of difference. Everything is exposed to those switching, that oscillation. Obviously, you don't want to be doing that too much in a domestic setting at very high powers. Otherwise, you're going to have a lot of neighbours complaining about their televisions not working and all those kinds of things. But I mean, the lab here is in an industrial setting, and it doesn't suffer from the same problems in that respect. So. That's my whole discussion of why I'm using wood. This is all plywood. This is oil lacquered, so it's varnished with an oil-based varnish, and that gives it a good finish, and also improves its characteristics electrically. It is important nonetheless, if you are going to use wood, is to obviously make sure that you isolate the high voltage parts from it. I mean, that's why I use these kinds of connectors, these high voltage connectors here, which essentially are all plastic through. They have a nice spacing, air spacing between the inner metal terminal and the outer plastic. So in that respect, you could work with the high voltage elements quite easily with wood as well. Okay, so that's the overall unit. What I'm going to do is I'm going to show how easy it is if I want to change the tube board. So let me just move this out slightly so we can see more of what I'm actually doing. It's better. Okay, so if I want to change a tube board, all I'm going to do is I'm going to just disconnect low tension, the earth, and just get a screwdriver. So the tube board is held down by 2 screws, one at the back here and one at the front. And I can just lift that away. As simple as that. There we can have a look underneath. These are the fans on the tube board, much larger of course than the 811As. I'll just put that aside for a moment. And now I'm going to bring the 811A board up and just get it the right way around. Put that one on. Put the 811A boards on and then simply reconnect it. Like so. I'm going to take this one off again, so I'm not going to fully connect it. I will put it back on later, but first of all we're going to have a little look inside. Okay, so I'm going to, and that's how easy it is to put different tube boards on here. Okay, so I'm going to bring this down again and then lay the unit on its side so we can have a little look at how it's arranged inside. So let me just bring this, readjust this camera. Say about there. Then I'm going to bring this round, lay it on its side, allow us to see. Probably. Maybe I just need to prop that up a little bit so we can properly see inside. Just okay, yes, so we can see in there reasonably. Okay, so we can see how it's laid out. I mean, it's quite compact. I wanted a compact unit that I could put on the bench top, which would allow me to control things quite reasonably, this gives you an idea of how it's laid out. So here are the 2 transformers. I mean, this transformer here is for the heater. This transformer is the grid screen supply. You've got your tank capacitors at the top here. For the grid supply, you can see the variacs, top, bottom, and the various interconnections. If I turn it up a little bit more, it probably allows to see. Let's put that in there. Okay, yeah, we could see a little bit more inside. At the bottom here, we've got the 15 volt low tension supply. We've got low tension transformers feeding the various measurements meters. They need to obviously be isolated, so they run through their own transformer. And of course, you know, the various output wiring, and the rest of it really. This is a soft start resistor on its own small heatsink. In the airflow, and also we've got a load here for the tank supply. So this is a discharge load, which is always connected for the tank supply. So when you turn the power off or you turn it back to zero, it will discharge this capacitor bank reasonably quickly. Relays here do the switching. I showed you the various ways that you could configure it for negative voltage, positive voltage, and across both positive and negative. Those are switched by these small high voltage relays in there, and then the rest of the resistors basically are really about the measurement system. We can see it in the top here. Here's the rheostat. Maybe if I lift it up a bit more, maybe I can prop it with that. Just hold it there. Yeah, there we can see we've got a better view of the rheostat, of capacitors, and the various interconnection and wiring. So it's a relatively straightforward unit, but nonetheless quite a lot goes into it to actually get a supply that you could use flexibly in this way. I'm going to be I'll take some detailed photos of these internally and put them onto the write-up page as well, so people can see how it's laid out. And also I'll be putting all of the circuit diagrams on there as well. But this gives, this is typical for, a research and development type supply. And this supply has turned out to be very reliable. I did have some initial problems getting the tank supply working properly with the measurement. You would change range and it would blow a fuse or something because too much current in the switching. But that's ironed out and with all the latest correct positioning of resistors and the values will be in the circuit diagram. So if you were going to build something like this based upon those kinds of diagrams, then you wouldn't have those kind of initial teething problems that I had to work out when I first put this together. We can also see here what I was saying about earthing. So these are the bolts that go through the transformers and the mountings for the toroidal. There is an emphasis here on having an earth wire here going down to the earth system. That feeds back into the line supply. Earthing also goes between the metal casing of the low voltage transformer, the various transformers here. They all have wired up earthwise the base of the bridge rectifier for the grid screen supply. Obviously in a metal casing or a metal housing, all of those would automatically be connected together by virtue that they are connected to the chassis, which is not the case here. Is what I was referring to earlier. So typically, I would say, apart from the very largest tubes, for example, I probably wouldn't run something like a GU5B off of this supply, but for all of the tubes that I supply, that I use, particularly for example the 833Cs, if you are doing high power Tesla experiments and research, things like transference of electric power, Tesla's radiant energy and matter experiments, those tubes really do take you right up to some of the most interesting. You can also drive Eric Dollard's cosmic induction generator using those tubes. You can configure them through the boards into push-pull if you want to use them like that rather than in parallel as they're wired at the moment. So there is such a wide range of flexible things that you could do with this kind of supply, and in a way, you put the effort in once, and you only really need to build it once. What I don't like is building lots of bespoke things, which I then dismantle, use the parts for something else. I prefer to keep together what I build, so that I can go back to them and experiment and use them at another time. And that was really what stimulated me to build a flexible base supply like this. Now this also has a plate supply that goes with it. I'm going to do a whole nother movie about that. I'm going to do a whole video rather on that, and a page, because that has a lot of detail. So normally a 5 kilowatt plate supply, so it is suitable for, and it's one that's suitable for powering all the way from, say, the small tubes, the 811As, which I use as a very good daily workhorse, right up to, for example, a GU5B, or pair of GU5Bs that you might use in something like fractal discharge experiments, Eric Dillard's cosmic induction generator, and galaxy in a bulb experiments, and then all the way right up further to pulse discharge experiments, for displacement experiments where you use thyrotron tubes. Thyrotron tubes typically running much higher voltages, say up to 15 kilovolts, say nominally for a medium power thyrotron, and to have a single plate supply that can supply all of those in a configurable way, that's very, very valuable and effective in the research and development environment, and that I will be covering in parts, plus also we will be looking at experiments running some of the more higher power experiments, some of the more interesting discharge and fractal discharge experiments and things like that using these power supplies. Okay, good. So what I'm going to do is I'm going to put this back together now, get it, wire it up, and we'll see how it runs. Okay, so I've connected this back up now. I've put the 833C tube board back on top, reconnected the connections at the back. I've put the line supply in at the bottom, and I've actually connected it to the Tesla coil as well. So just turning on main power at the back, that will bring on the 2 digital meters. It's actually got the 15 volts. I could turn the fan on, so we can hear a fan running on the box. I'm just going to turn that off for the moment. Or we could run the fans on the tubes. So now we get airflow out the top, coming out, it's collimated up over these 2 tubes. I'll just turn this off as well at the moment. Okay, so for the heater, first of all we've got to engage the heater. So we make sure it's wound down, we turn on the heater supply, and then for the 833Cs we're looking for 2 in parallel. Nominally each they are 10 volts at 10 amps. So we've got these 2 connected in parallel. So we're going to expect around about 10 volts AC at 20 amps. We're on the 20 volt scale, so I'm going to start winding up. Let's make sure we can see that on the camera. Yes, we can. Start winding up. Voltage rising. Doing it nice and slowly so we don't go over at any time the 20 amp. We can see the glow starting to come on the tubes. Okay, so just coming up. 20 amps. There we see why the digital setting is so nice. The meter just slightly over the centre mark. About 10.5 volts. So there'll be at 20 amps. There's going to be a little bit of loss between the output of the transformer and the base of the tubes. When I measured those more accurately with an AVO connected across the connections to the heater directly, it comes out at about 10.2 volts. So nominally pretty much straight down the line. If you want to see, if I put it in soft, okay, we're going to see, because that resistor's now been switched in to the primary circuit of the heater transformer, the voltage has dropped slightly and the current has been restricted. So had I just want to turn that on, for example, if I now turn that off, Now I've got it set in the right place. If those tubes were cold, I can turn on in soft start. Never goes above 20 amps. Obviously they are warm now. And then I switch it over to full when they've warmed up, and it's nominally back on the 20 amps. So that's the heater supply, and we can see the heaters alight here. Now this is actually set up for a feedback oscillator, so we don't need to use a grid or screen supply, but if we were using it, then again we turn this on. First of all, we're going to set our tank voltage. So that is the voltage is the tank capacitors after the bridge rectifier at the output for the high voltage toroidal transformer. So that forms our tank. Basically, it's our reservoir for biasing this and keeping it stable. We're not using any other kind of regulators, for example, semiconductor regulators or anything like that. I have found that to be notoriously unreliable, especially when you're working with switched pulse experiments and switched circuits using tubes and stuff like that. Semiconductors just don't go well together with high voltage and switch circuits in that way. For example, you switch a tube, in certain configurations you can be left with a plate voltage coming out the cathode, and that's incident on some kind of semiconductor switching, and that's the end of your semiconductor. Make sure that you have a big bag if you're going to do that kind of thing. So rather than use semiconductor regulators in this, I went for a much more straightforward adjustable bias. Obviously, as load changes, you do have to make changes to that bias as well, but once you get it set up in the right operating position for a particular experiment you're doing, then you can just leave it there. And that's the advantage of using a separated tank and then an output bias control. So we've got it set to tank, we've got the tank set on 500. I'm going to raise the tank up there, the needle's gone up to 100 volts. Obviously there's no current being drawn. I'll take the tank up to 200. The tank is up 200 volts. So if I now switch us over to the output, so the output is currently on 100 volts full scale deflection, and we're reading 50, and we're in a central point. If I go fully up to the high point of the adjustment, we're now showing 0 volts. So because we've got our output setting from 0 to minus 700 for full tank, in effect we are now set from 0 to minus 100. That is a range of available biases. So if I bias it all the way down to its lowest point, all the way down there, minus just a tad over minus 100. We go back to the tank. Tank sitting just a tad over 200. So if I just bias that down, back out to the out, it's minus 100 volts. But if I want to set minus 50, now I've got the tank set. If I want to set minus 50, I can set it there. I can also do it much more accurately. I can go down to, so there's 50 volts. Let's wind it actually right back to 0 and go right down to the lowest scale. Now that's 2 volts, minus 2 volts, minus 4, 8, 12, 16, 20, minus 20 volts. And the control is very controlled. Quite large movements of this rheostat lead to small changes in the voltage. If I go right back up, put it on the 200 range, it's 100 volts, which was 100 volts is half of our tank, because we are using one secondary coil, the lower secondary coil. If we go back to the tank was set on 200 volts. So that controls the scale, the range of the bias that's available at both ends. So 200 nominally in grid arrangement would give plus 100 and minus 100. So plus 100 volts to minus 100 volts. We are operating in the negative side of that bias only, so from 0 to minus 100. And so we would expect there's 100 volts. That is our maximum bias, minus 100 volts. There's the tank. Okay, now turn it off. It's discharging the tank. That's what those discharge resistors, power resistors were for, to make sure that that will discharge. Now we're going to switch it over to plus and minus. So we're going to use it. Now we could go between plus and minus. We're using both coils, both secondary coils. So first of all, we're going to wind the tank up. Let's take the tank back up to 200 volts. So that gives us nominally plus and minus. So now I'm using plus and minus. I'm going to place our grid adjust in the middle of the bias. Change ourselves to output, and here we should be able to adjust it around 0. Okay, so now in 0. Now it's more negative. So there's 100 volts negative. 0, starting to go positive, so we've flipped this over to positive. Now we're going plus 100. So we can control that very accurately. Put it into negative, that's negative voltage. We wind the grid adjust down, negative voltage, switch over to positive. That's now positive voltage. So we are going plus or minus 100. There's a 0 point. I can change that bias very accurately. Let me put it down to the smallest range. Plus 2 volts, plus 4 volts, plus 5, plus 6. That's how accurately we can adjust this, and that's what makes it very good in a research scenario. Okay, go back once again, grid fully up. Back to 0, we go negative, minus 100. Put that back in the middle, go back to the tank, wind the tank down, so there's no tank. Switch over, back to the negative. These are locked because, as you can imagine, if you knocked one of those accidentally, you could change the whole bias. If you've got a tube running at power, suddenly the bias changes, well, that could be not a very nice day. So that's why these are locked. They can't move. Wind the tank back up. 200. We can take some very, very high tank values as well. If we wind fully up, 500 volts tank. Now if we have a look at our voltage range, I'm going to wind that fully 0 first of all. We look at our output voltage. I would expect, let's put that up at 500 volts. I would expect to be able to wind that all the way to the middle. So minus 250 volts now. Ultimately, we can use the tank very high. So if I go back to looking at the tank, put it on 2K. So the full output of the transformer, that is now about 500 volts. If I wind it right up, that's right up now at 1.5 kilovolts. Full tank. Great for a screen. Let it bleed away, those discharge resistors. Typically, for grid bias, I operate somewhere around here. 200 volts tank, 100 volts grid adjust, bring it on the output, there's on minus 100 volts. Bias for an oscillator, somewhere around about there. Class C, just turned off, and then we're going to put an input, pulse input, and operate it as a Class C amplifier, non-linear amplifier. So I think that gives a good idea of how bias works. If I wanted to use the full 1.5 kilovolts out, if I got the tank right up at 1.5 kilovolts, then an internal switch, there is an internal switch in there, which I can switch over, which references the black ground, or the negative terminal of the section on the back panel, which is for the grid screen output. That will be referenced to the bottom end of the secondary coil. So you then get, in 2 coils in series, you basically get the full almost 1.5 kilovolts available in one range. Switch the switch back to the center, it switches the reference point back to the center tap, and then we are talking about plus or minus 700 to 750, which we use for our grid source. Okay, so tanks down. Obviously, if we had a load on there, we would also be showing milliamps. So this will take us up to 200 milliamps output. It can also show us our grid bias. So we've got a grid connected with a resistor. We're going to see our grid bias there. Obviously, that's only in the DC state when it's first set up. This meter is not useful, obviously, for the RF grid bias. It's only for the DC bias milliamps. Okay, so I will use this grid screen in an experiment, and then I'll show how that's actually set up in an experiment, say with sort of 400As being used in push-pull for, say, an induction generator experiment, and then I will show how to set up that bias using this section. For the moment, we turn that off because we're not using it in this experiment. We notice that whilst these have now been heating up, I'm going to put the fans on. Bulbs now will be quite hot. And we notice that also we need to adjust this bias slightly back up now that they've all heated up and settled down, back up to 20 amps. And I'm going to use, let me change, just pan the camera around a bit so we can see the experiment as well. I can get them both in. Yeah, I can get, I think, everything in. Let me just pull it back slightly. That's it. So we've got the whole experiment. If we just look at the experiment there, single wire load, cylindrical coil driven by this tube supply. We've got the normal instrumentation up here. We'll show we're showing power, and we're showing, we'll see the signal and obviously the frequency that we're oscillating at. So just going to put this back on here for the moment so we can see the experiment. I'm going to be using the high voltage supply for this. So our bias is set about right. We're just on 20 amps there. Everything is connected. The high voltage supply, and you saw over here on the right hand side, that takes power off down the line here, comes down here through to the coil, back from the coil, primary coil, through the tubes, and everything is referenced to line ground. The feedback from the coil feeds back to the grid, and that forms an oscillator circuit with the grid elements that I've added here. So if I turn on the high voltage supply, we'll wind up some tension. Here's the coils running. Quite low, just at 300 watts. It's not very, you don't need much to get it all oscillating. So that's the pair of 833Cs. Running as a linear feedback oscillator. Looking at the equipment here, so we're running about 300 watts, oscillating about 2.65 megacycles. At the upper parallel resonant frequency, the upper parallel mode, we are oscillating, although we can't see on the camera, the neon bulb is brightly lit at the top end of the secondary coil. We would expect the waveform across the primary. We're measuring with a high voltage probe there across the primary terminals. That's showing us oscillating as a slightly distorted sine at about say about 1200 volts peak to peak. We're applying, if I wind up the power a bit further, it's about 500 watts. Plate supply is only at 1.6 kilovolts. 2000 volt peak to peak oscillation across the primary, just over 500 watts in. Single wire load, very, very brightly illuminated. That's just getting off the starting blocks for a pair of 833Cs. They're hardly even doing anything. They're just oscillating their low power. We could push those up much higher from those for that pair. We would aim, if we were putting those on a 4 kilovolt plate supply, we would expect to be able to transfer around about 2 kilowatts, 1.5 to 2 kilowatts of power. We will be able to push down the TNT system into a load at the other end in the midfield region. Quite a nice powerful pair, 833Cs. They have the graphite plates, makes them better at high power. They have the better thermal properties, and when you're really pushing them hard, you can get those plates glowing. We'll be seeing that in some of the future high power discharge experiments that I'm going to be doing for the displacement side of the work. So there we are. Let me pan round so you can have a look at the other side of the experiments. Let's look at the instruments. There we are. See, we can see just over 500 watts. If that comes out on the camera, you can see the oscillation there, and the counter is reading 2.659 megacycles. The upper parallel resonant frequency. Good. So what I'm going to do is I'm going to turn that off, and I'm going to now, say I decide that I want to move to the 811A board. I'm just going to let those cool down a little bit. I'm going to leave the fans on. And wind that back to 0. And I'm going to show now the value of being able to move from one tube board to another. Just let those cool off a little bit. better. Then I'm going to turn off this unit, unplug from the line. I'm going to disconnect. The high tension was already turned off. I'm just going to flip the circuit breaker, disconnect this, disconnect the feedback, and we can turn this round so we can expose the back connections like so. Disconnect those, disconnect the earth, ground for the oscillator, disconnect the low tension. Find my screwdriver, where I put that down. Okay, so I'm going to remove the screws. That one screw up there. We can lift away that tube supply. I'll pop it over the end at the moment. And we bring this one in. Pop it on top. Put the screws in. That line. Screw in at this end. Now we reconnect. Don't lose those, I'll put them back on the other tube board. Just put that tube board back over here. Right, so we connect the heater. Connect up the earth, connect up the fans. That's it. So it's back fully connected. Everything else is the same. Okay. Pop that back. Okay, just had to change the battery on the camera. So let's just go back to where we were. So I've changed the tube board to the 811As. I've now reconnect the plate, reconnect the feedback coil to use it as an oscillator, reconnect the line supply at the back. Okay, turn on. So we are essentially reset, but in very short space of time. We've now changed completely our tube supply board. Just check where we're set to oscillate. Looks reasonable. Switch back over to 10 volts first of all. So we've got a quad 811A. Nominally one is 6.3 heater, 4 amps. So we're looking here to wind this up to 6.3 volts at 16 amps. Make sure that's off. It's on full, not in soft. Turn on, and now wind up. Increasing, 11 amps. Always keeping it underneath the maximum, 12, 13. Voltage is coming up. Approaching 6 volts, 16 amps, there we are. we see all 4 of the heaters have come on. Let that stabilise a little. Let it warm up. Always a good idea to let valves or vacuum tubes settle down before we actually start using them or pushing them. So this now also gives an indication of how easy it is to set a different set of tube heaters just by winding the variac to the right position, checking the current, make sure that it's what we would expect for the voltage. So nominally we're just over 6 volts there. That will adjust slightly as things settle. I'll turn the high voltage supply back on as well. And now we just wind up. See, there we go. Going to readjust the tuning on this one, so more effective on the lower. There we are on the lower. Of course, pushing less power than the 833Cs. Just optimise that. So that optimal there. 300 watts. 300 watts at 1.858 megacycles. So now we're at the lower parallel mode. Driving it with a quad 811As, just 300 watts. And only 600 volts on the plate supply. Already well illuminated in the single wire load. Go up to 500, very well illuminated. In this range, the 811As, like the quad 811As, could drive just as well as the 833Cs. Of course, they haven't got anywhere near the top end power. The 811As will run out somewhere around about a kilowatt, whereas the 833Cs are going to head on and push an even further kilowatt. At 300 watts. I'll just pan round so we can see the instruments. There we go. Everything in. So 1.858 megacycles. Similar kind of voltage, potential across the primary coil. It's about peak to peak. Just check that range. Yeah, probe's 1000 to 1, which it is, high voltage probe. So around about 1500 peak to peak, 500 volts a division. Runs very easy, very stably. Put the fans on. Just turn off for a moment. You can feel the airflow coming out of each of those, cools the tubes very nicely. Back on again. We're going at 1.858 megacycles again. See here, just under 300 watts. We'll just adjust the high voltage supply, which you can see down here. By the way, that's the high voltage supply. It's coming out through bridge rectifier, it's going through the discharge unit. Discharge unit just lets me kill the storage on the capacitor at the back if I wanted to. Come back around to the experiment. There we are. So what I wanted to show there was how easily in a versatile unit you can swap from using one tube board to another. We could change configuration, run them in different ways, and of course you could even build a custom board there. These are generalized boards that I'm using for a range of different experiments, but you could build a custom board if you want to do something special, build a special circuit. Well, you've got a board that you can put on the top there, and you have all the available biases and heater supply, and the measuring and the monitoring of this required to drive tube experiments. The other part is the plate supply. I will be going through that in a lot more detail, but otherwise I think this gives a good idea of, when you have a versatile unit like this, how easy it is to work with different tubes, work with different experiments and configure them in different ways. And in subsequent posts where I'm doing other experiments, I'll be using this unit a lot in some of those experiments, like induction generator experiments and pulse discharge, very specific displacement experiments with thyrotrons and things like that. I'll be using this setup and showing how to configure it and set it up to run with various types of experiments. But that'll come as part of the experimental work. I just wanted to introduce here this unit and how that unit can be used in relation to different types of tube configurations. Okay, good. So really that's the end of this video. I'll be providing the normal detail in the write-up that I do. I'll also be putting pictures. I'll be taking pictures after this video now of all of these items, so you can see in more detail, and obviously I'll be providing the circuit diagrams as well. Great. Okay, good.